Okay. It's recording now. Okay, as I said, first quiz is on Monday in class. And that's 1 week from now, so that would be September 17th. Okay, so today I'm going to do a few things. The first thing I'm going to do is do a very quick review of integration, because I know some of you are learning calculus or are not so comfortable, or you've learned calculus but you're not so comfortable with it. So let's just do an integration review first. All right, so let's suppose I have a function f, that's a function of t, and then I have another function g, that's a function of t. Now, let's say if the derivative of g with respect to t is the same thing as f of t, the derivative of g is equal to f of t, then we say that g of t is an antiderivative of f of t, meaning that it's like going backwards. It's not taking the derivative of t. So taking the derivative of g gives you f. So going from f to g is sort of the reverse. That's why we say it's antiderivative. Now, one thing I should mention that, note, g of t plus c would also be an antiderivative of f for any constant c. Okay, why is that? Because if the derivative of g is equal to f, if I take the derivative of g plus c, it's also equal to f because the derivative of the constant is 0. Make sense? All right, now, so we can define the integral of f. So the integral of f of t from the starting point, let's say t1 to time t2, okay, the integral of f of t from these two times is, we use this symbol, the integral sign, which is basically just a summation, meaning the limit is you take little pieces of time intervals. And we have t1 to t2. This is the bottom limit of integration, that's the starting time. And this is the top limit of integration, that's the end time. And the integral is f of t dt. Okay. Everybody's good on this? And that is going to be the antiderivative function, g of t. And I'm going to use this notation. I'll just have a half, just a line on the right side, and t2 up above and t1 below. And this symbol means you evaluate the function g at the top value, t2, minus the value at the bottom, t1. Okay? That's just the definition of that. So this is how the integral works. You take the integrand, you find the antiderivative of the function. Any antiderivative would work. And then you evaluate that antiderivative at the top value, the end point, minus the value at the beginning, or the starting point. Okay. Questions about this? Everybody's good? How many of you are seeing this for the first time, by the way? Okay, a few of you are. All right, are there any questions? You had a question? Yeah. Okay, so that's a good point. Let's do an example. Suppose I have the function f of t is equal to t. All right? But then an antiderivative, I need to cook up a function such that when I take the derivative of it, then it gives me t. Okay? So I know how to do that. If I do t squared over 2, if I take the derivative of t squared, I get 2t. but the 1 over 2 sitting on the front to cancel the 2 that I will get. Okay, so that will give me t. So if I do the integral from t1 to t2 of t dt, then you say, okay, I take my antiderivative guy, t squared over 2, and my limits are t1 to t2. And so I end up with t2 squared over 2 minus t1 squared over 2. Okay. That's generally how it works. Questions about that? Okay, now the meaning of the integral. So this thing t1 to t2, the integral of f of t is the integral, this is the area, and I will actually qualify this a little bit later, the signed area. So plus and minus signs will take, there'll be some plus signs and some minus signs that I'll tell you about later, is the area under the curve f of t. Okay, so let me show you how this looks like. If I have the function f of t, and I plot it, here's t, and then there's f. Let's say it's some curve like this, and I have my initial time t1, my final time t2. Then when I say the area under the curve, first I find where 0 is. It's that region from the curve to 0, and the beginning time to the end time. It's this area here. This area is equal to the integral t1 to t2 f of t dt. Okay? Anybody have questions about this? Now, if the curve was negative in some region, if the curve goes below 0, the integral will be negative. So it's not just an area. There's plus signs and minus signs depending on whether you're above or below the curve. Okay. So if I have this curve here, yeah, thank you. Very good. T1, T2. Let's make this go a little further. And then I have this area here. Okay, so this integral from t1 to t2, f of t dt, and this region is negative. It's still going to be the area under the curve, but you put a minus sign because it's on the other side. Okay. Any questions about this? Good. So that's why I say you can think of it as the signed area under the curve. So it's not just areas where all areas are positive. If it's below the curve, it's a negative area. Okay. Is anybody confused about this? Yeah. Your question? Okay. Good. Let's go on. Next thing we'll talk about is more vectors. So vectors continued. We've already started this. I'm going to repeat some stuff from last time. So let's say we're going to add two vectors together, A and B. And A looks like, let's keep what I had before. A looks like this. And B looks like this. Then to add A and B, remember you take your first vector, you draw it. That's my A. And then so this is what I call the starting point. And this is the endpoint of A. From the endpoint of A, I draw B. Okay? And then this is going to be the final endpoint. And so going from the very start to the very end, that is going to be my A plus B. Okay? Are there any questions about this? Now, if I want to do A minus B, then I have A here. And I have B. Okay, the first thing we'll do is we'll take the negative of B. So it just goes in the opposite direction, just like this. That's minus B, negative B. And then if I want to have A minus B, it's A plus negative B. Okay. So we draw the first vector. So the first vector is A. We draw it. And then, remember that's the starting point. This is my A. And then I attach B, negative B to it. So I start from the end of A and go to do my negative B. And then I have my final endpoint there. And then I go from the very start to the very end. Okay, and that's A plus negative B, which we said is A minus B. Okay? Any questions about this? You just keep track of starts and ends. This is pretty straightforward. Now the new thing we'll talk about is if we multiply by a number, okay, if m is a positive number, okay, so sometimes you will hear the word scalar. Scalar just means not a vector, it's just a number. Okay. Scalar means a number. If m is a positive number, or it's what we call a scalar, then m times a, multiplying m times a, is a vector with magnitude. So remember, that's how long the vector is. M times magnitude of A. So remember, that's the symbol for the magnitude of A. So what I'm saying is if I multiply some number like 2 to A and I get 2A, then the magnitude of 2A will be 2 times the magnitude of A. That's not particularly surprising, right? Okay. So it has magnitude m times magnitude of A, and points in the same direction. Points in the same direction as A. Okay, while I'm talking about positive numbers, let's also talk about negative numbers. If m is a negative number, then m times A is a vector with magnitude. Well, I can't just say m times A, because if m is negative, then I will get a negative number for my magnitude. So in order to, magnitudes are always going to be positive or 0. So I'm going to put an absolute value in front of this guy. Okay, an absolute value. And then this will be the magnitude of m times A. Okay. But because m is negative, it's going to reverse the direction. It's going to go in the opposite direction and points opposite to A. All right, so let me now make some drawings that will make it clear. So here's my A. If I want to have 2 times A, it's going to be twice as long, pointing in the same direction. If I have 1/2 times A, it will be half as long, pointing in the same direction. If I have negative 1/2 A, it will be going in the opposite direction with half the length. If I have negative 2A, it will be this big vector going in the opposite direction. Is everybody good on that? Okay. Any questions? All right. Now, before we go to the next topic, maybe I'll break it up and I'll mix in a clicker question before we go to the next topic. Okay, so let's do some example with motion and velocity. Example 1. Let's have a plot of the velocity in the x direction versus the time. So this means time in seconds. T is measured in seconds. And then we have Vx, that's the x component of the velocity. And that will be measured in meters per second. And let's say this is 0, 2, 4, okay, 6, 8. And then we will have 5, 10, 15, 20, 25. And let's say we have this point here, 20. So this is 20, 28. So I'm trying to line it up so it's nice. But the curve itself is going to look like this. Go to this point, and then it'll come down to this point over here. And the question is, find the displacement in the x direction. There's only one direction in this problem, so that's the same. From time t equals 0 to time t equals 25 seconds. Okay, the whole time interval. And let's say A is 10 meters, B will be 18 meters, say C is 50 meters, D is 80 meters, and E will be 100 meters. Okay, and I'll open up the colon. Press AA if you need to do that, but let's go. Okay, we're plotting dx, the x component of the velocity. Okay. Give you a few more seconds. All right, if you haven't already made a choice, go ahead and make your choice. And let's see what people have said. All right, a lot of people said E. That's good. I think people know what's going on then. The displacement under the curve is the area under the curve, sorry, displacement. Remember, displacement, the relationship between displacement and velocity. The derivative of the displacement is the velocity, so we say the displacement is the antiderivative of the velocity. So if I'm doing integral of the velocity, that will give me the displacement. Okay, displacement is the area under the curve for velocity versus time. Okay, so we need to calculate the area. So we have this point here. We said it was 8 meters per second. Okay, and we had like this, and this one was 20 seconds. And then we had a 5-second interval, and it went down like this. Okay, so the area of the, so we have these right triangles, area of the triangle is 1/2 the base times the height. So half the area of a rectangle, same base and height. And that's what we'll use here, area. We have base is 20, height is 8, so we'll have 1/2 20 seconds times 8 meters per second, plus 1/2 base for this triangle is 5 seconds, times the height is again 8 meters per second. And then we get, this will be equal to 80, this will be equal to 20, so we get 100 meters. Okay? Any questions about this? All right. Good. Let's go on. Let's do a similar problem. Same sort of graph, but let's have it a different plot. This time it will be x in meters. It will be time in seconds. And then we will have 2, 4, 6, 8, 0, 5, 10, 15, 20, 25. And the plot will be the same as before. And then it will come down. And the question this time is, find the instantaneous velocity at t is equal to 20, what do we say, 22 seconds. And the choices are uh, 0.8 meters per second, minus 0.8 meters per second, 0 meters per second, and 1.6 meters per second, minus 1.6 meters per second. Okay? Go ahead and make a choice. If you haven't made a choice yet, go ahead and do that. Okay, let's see what people said. All right. But a lot of people get B. So let's check that. Okay, so instantaneous velocity. Now, we're going to use the fact that it's a straight line, or you assume that I did my best to draw a straight line, and it really is a straight line. Okay, so if it's a straight line, the instantaneous velocity is the same thing as the average velocity and the interval, right? The reason is that it will be constant velocity along any straight line. Is everybody comfortable with that? If I'm plotting x versus t, and you have a straight line, that's constant velocity. Okay, so I'm going to take these 2 points, 20 seconds and 25 seconds as being the initial and the final time. So I can calculate Vx, all right, by taking delta x over delta t. And I can choose a rather fat interval because it won't change the answer because it's constant velocity. Okay, so the delta x, the final is 0 meters. That's the final. The initial is 8 meters. Initial. And then the final time is 25 seconds minus the initial, which is 20 seconds. So I get minus 8 meters divided by 5 seconds. And that's minus 1.6 meters per second. Okay? Any questions about this? Everybody's comfortable? All right. By the way, if you're wondering why I do relatively easy questions in class, my general strategy is I try to ramp it up. So I'm trying to make sure everybody's on the same page. It seems like people get this, but it's going to start to increase as the week goes along. Okay. All right. Now let's go ahead and do the new topic. We're talking about components of the vector. Okay, so life so far has been kind of simplified because we were in one dimension, but now we have to consider having more than one dimension, and we have to work with components of vectors. And here's that trigonometry stuff we were reviewing before where it will come in. So we have, let's say, it will suffice to work in only 2 dimensions. Of course, we live in 3 dimensions, but we'll just take 2 axes at a time. So my plus y, my plus x, and my plus y directions. Let's suppose I have a vector like this, A. What I can do is I can break A into its components. So I have this piece that I will call AX, and then I will have this piece which I will call AY, and these are the x and y components of A. AX is the x component, and AY is obviously the y component. Now we can even just write a notation as AX comma AY, just writing the components. That's one way of denoting a vector. Sometimes in some textbooks you'll see funny brackets, like angled brackets, but that doesn't really matter. But now let's make a connection to geometry. So I have this right angle. X and y axes are perpendicular, so that's why I have this right angle. And one key point is when you do the components of the vector is always the hypotenuse, okay? So if you ever are doing components and resolving a vector, and the vector is one of the legs of the triangle, these things are what are called the legs of the triangle, you're doing it wrong, okay? The vector is always the hypotenuse. So the vector A, in fact, let's say the magnitude of A is the hypotenuse of the right triangle. It's always going to be like that. Okay. All right, now let's remember our trigonometry. Let's call this angle theta. Then if I'm going to do the cosine of theta, Cosine of theta is the one with the adjacent side, so that's adjacent side is ax. So it's going to be ax divided by, and I said the length of this leg here will be magnitude of a. Okay? Any questions about that? So if I want how long this leg is, it's just how long a is. Okay, now I have the sine of theta. That will be ay, because that's the opposite. Sine is the opposite. So it's the opposite divided by the hypotenuse. So that's ay over the magnitude of a. Okay. Now we're going to do this many times, so you probably will just skip this step and then just cross multiply. So I'm going to, or either cross multiply or multiply both sides by a, magnitude of a. Then I will have ax is equal to the magnitude of a times the cosine of theta. Everybody follow me on that? Okay. Just multiply these guys, and I have ax is equal to a magnitude times cosine of theta. And then I have ay is equal to a magnitude times the sine of theta. Okay, so typically we will just jump to the step. The way I think of it is cosine goes with the adjacent. So if I multiply cosine to the magnitude of the vector, I get the adjacent side, which is the x component. If I multiply the sine, which goes with the opposite leg, times the magnitude of the vector, I end up with the opposite. So the way I've drawn theta, then it will be the y component. Okay, so there's one other thing that I might note also. The tangent function, the tangent, is the ratio of the opposite over the adjacent, so that's ay over ax. And so if you want to solve for the angle, sometimes they'll ask you what is the angle, and so theta is equal to the arctangent, or, yeah, thank you, is the inverse tangent or the arctangent, ay over ax. However, when you calculate, when you do arctangent on your calculator, let's see, here's my calculator. If I do If I do arctangent, so that's my arctangent, and let's suppose I have 0.5, or I don't know, I just made up a number. I get 26.56. When you do arctangent, don't completely trust your calculator, because it's only giving you the answer plus or minus, possibly plus or minus 180 degrees. Okay? The reason is when you do arctangent, the point I'm making is if I added 180 degrees to the answer I get and take the tangent of that angle, it'll be the same thing as the tangent of the original angle. Okay, so there's an ambiguity, which kind of scares people because they don't know whether they have the right answer or not. So let me just say this. Be careful. You may need to add or subtract 180 degrees to the answer your calculator gives. Okay? And then the question I may have is, how do you know what to do? How do you know maybe the calculator gives the right answer, maybe it does not? So let me give you a very simple example. Suppose I have ax is equal to 5 and ay is equal to minus 5. Okay, very simple example. And so now what I will do is I will do theta is equal to inverse tangent or arctangent of ay, which is minus 5 over 5. So inverse tangent of minus 1. Now let's do that. So I will have inverse tangent of minus 1. And then I get minus 45 degrees. Now, question is whether I should trust that or not. The very simple thing to do, okay? So by the way, there is a convention that I should mention, that we measure angles counterclockwise from the x-axis. So are you familiar with that convention? That's the standard way of doing things. So if it says it's negative, that means you're actually going in the opposite direction by that. Okay? All right, let's just check this. Well, we can just simply draw. So the answer to how to figure out which way it's pointing is you just make a sketch of it. So if ax is 5, it's 5 in the positive, it's 5 positive in the x direction. Okay? And then it's negative 5 in the y direction, and this is the angle. Okay, that's what A looks like. And it sure does look like it's minus 45. It got the right answer. My calculator gave me the answer I wanted. Does that make sense to everybody? Okay. But it may have been on the other side over here. For example, if ax is equal to minus 5, and then ay is equal to 5, then what I would get is that theta is equal to arctangent of plus 5 over minus 5, and I would have ended up with minus 45 again, but I would have gotten the wrong answer. You see, the reason is if ax is minus 5 and ay is 5, if I just make a sketch, in other words, you just spend a few seconds to figure out this is my minus 5 here, and this is my plus 5 now. So this is the vector I need. This is my A. And you can see that angle is not minus 45, but rather it's 135. And so what I need to do is I need to take the answer my calculator gives, and I would need to add 180 to it, and that will give me 135. Does that make sense to everybody? You just sometimes have to add 180s or subtract 180s. All you need to do is make a little sketch of where the vector is pointing. Okay, next thing. All right, I said a magnitude is a hypotenuse of the right triangle. Right triangle. And so it's equal to the square root of the sum of the squares of the legs of the triangle. So ax squared plus ay squared. Questions about this? All right, now we get to the main reason why we're doing the components, and that's because when we add vectors, we add components together. So adding vectors with components. So this graphical thing was kind of limited use. So let's say vector C is equal to vector A plus vector B. The way we will do it to add the vectors is we just say the x component of C is equal to the x component of A plus the x component of B. The y component of C, as you can guess, the y component of A plus the y component of B. Okay. So if I'm just add up the components for each direction, just add up components for each direction. So if I write this notation, A is equal to ax comma ay, B is equal to bx comma by, right? And then C, which is going to be A plus B, this will be, you add up the x components, and then you add up the y components. Questions about this? All right, that's not so difficult, I think. Now, next thing we'll talk about are unit vectors. So, a unit vector. How many of you have heard of unit vectors someplace? Okay, half of you. All right, a unit vector is a vector with magnitude equal to 1. Okay? So if you take any vector other than the zero vector and divide it by its magnitude, you end up with a unit vector. But I'm going to focus on a couple special unit vectors here. Okay? So the unit vector in the plus x direction, and that is called I with this caret hat to it. Okay, so it's just a convention. X goes with I. And the unit vector in the plus y direction is j hat. Just a convention for that. So if I want to draw a picture, here's plus x and plus y. Then if I just have something of length 1 here, that would be my I hat vector. If I have something of length 1, that would be my j hat vector. And now I can actually write down a formula like this. The vector A is equal to ax times I hat. It stretches the vector by an amount ax plus ay times j hat. Okay. So I can see that just by drawing something like this. I have my vector A. This vector here will be ax I hat. Oh, thank you. I like your reflexes. That's pretty fast. Okay. And we have ay j hat. Okay. Does that make sense? If I add these two together, the start to the end, that gives me A. Are there any questions about this? These are key things we'll use over and over again. By the way, don't be. I know it's a huge class. It's a little scary asking a question. You're afraid it's a stupid question. The instructor will make fun of you. No, I'm not going to make fun of you. If you have a question, just ask the question. Okay? Yeah. Okay. So you can't tell from here, but if I did something stupid like put the number line, now you can see it's 1. Okay. That's all. I just didn't label them. Okay. Now, last thing I want to mention. Just take a minute. So I want to mention speed, and I apologize, I meant to say this before the homework set that you did over the weekend, but it's coming now. Speed is the magnitude of the velocity. Okay? It's just how big is the velocity. Don't worry about plus signs, minus signs, or directions. In one-dimensional motion, then we only have, let's say, the x direction, the magnitude of the velocity, that's the symbol for the magnitude of the velocity, that will be just the same as the absolute value of the x. Okay? But in two-dimensional motion, this is the last thing we write down. In this case, it's the more complicated formula because we have components in both directions. It will be vx squared, this is a v, plus vy squared over square root. Okay. Any questions about this? All right. I apologize that today I won't be able to be in the help room after 4 because there's an important faculty meeting. But if you have any quick questions, I'm here for the next few minutes. So I'll see you guys tomorrow.